Go.
All right, good afternoon, everyone. My name is Alex Andreessen, and I'm with my partner Kelby Escobar here, and we're here talking a little bit about our project, go over our proposal a little bit. So our title is using an energy storage system to estimate inertia in a power system. Jumping right into the outline here. We're going to first talk about, we're going to give you a brief introduction to our problem. We're going to give you our motivation for our project as well as a little brief description. We're going to go over some background information about what has been done in the past and how we will be combining that with our current project. Then we'll go to the scope of the project, what we're doing and what we're not doing, and then the objectives or the goals we're trying to reach. After that, we'll go talk about the technical solution. We have a block diagram as well as a four-step process to what we'll be implementing in general. And then we'll close with the timeline and budget, and then we'll open it up for questions and closing thoughts. I'm going to go here and talk about a bit of a brief introduction about what our problem is. So as the U.S. power grid is acquiring more and more solar resources, there will be a decrease in other generation methods, cause and effect there. Things like coal-fired and natural gas rotational turbine generators are becoming decommissioned as they emit harmful wastes. That leads to an overall decrease in system inertia in a power grid. Well, that isn't necessarily a bad thing. It can lead to some unpredictability and stability issues. So we like to remedy that by being able to calculate that inertia constant in real time in order for control engineers to develop a way to regulate that system frequency in order to improve stability and overall system health. So with that, I'm going to turn it over to Kelby here, who's going to talk about the motivation for our project as well as the description. Go ahead.
I'll be talking about the project motivation. I would say the project motivation mainly stems from what Alex is saying with how solar is becoming more prominent in today's age of power, as well as renewable energy sources. For example, this can be seen in California as they're implementing mass amounts of solar power within their power grid. With this implementation of solar into their power grid, this requires a different control strategy, not only in California, but everywhere else too. Why does this requires a different control strategy? Because solar is definitely safer for the environment compared to traditional non-renewable energy sources, which is harmful for the environment. So by using a different control strategy, solar power can be distributed more efficiently to consumers, which would in turn be safer for the environment and lead to a reduction in harmful emissions, which happens with traditional energy sources now. One way that we're going to be looking into doing this is by studying the rotational inertia constant and using that value to estimate the inertia constant. So a little brief description about what we're going to be doing. So our goal for this project is to estimate this inertia constant in our power system within plus or minus 10%. We're going to be doing this by sending in an active power signal into our power system, which is going to disrupt it and the frequency as well. With this disturbance that's happening, we're going to receive feedback with the OPRT, and we're going to get the measurements of the voltage and current from sensors. And with these measurements taken, we're going to use our OPRT or the OPRT system and the algorithm that we're going to implement, and we're going to derive this inertia constant from the voltage and current measurements that were taken. So here's a little background of our project. So from previous years, this inertia constant was previously estimated via simulation using MATLAB and Simulink, and a technique called moving horizon estimation, which I mentioned in the previous slide. This moving horizon estimation, or MHE, is defined as an optimization approach that takes numerous measurements over time, including noise, and using those measurements and estimates an unknown parameter. So in this case, that would be the inertia constant. And then within that project, within the previous years as well, they tested out different excitation signals or probing signals to disrupt the system. And they found that the square wave resulted in the best results for the project. There were many different waves tested as well, but this one just came out on top. And also, CAN communication system was designed for communication between the Opal RT and the power system as well.
All right, we'll talk a little bit about the project scope. First, talking about what's in scope. We have an energy storage-based system to estimate inertia. There's other methods out there. We are using a battery inverter combo to send the excitation signal to disrupt the system. That is one approach, and that's what we'll be doing. Next item is an implementation of an algorithm to estimate the inertia constant within 10%. And finally, the integration of a commercial inverter with the other components of the system. We will be using a Xantrex inverter that is already in Microgrid Lab, and interfacing that component with the other components is in scope. Talking about out of scope, a method to regulate and control the system. We will not be doing that. In actual practice, you would want to use the inertia coefficient we're solving for to regulate and control a power system. That's not in our project description. Next, we won't be designing a converter or any individual components. They're all provided for us, and the implementation on a dedicated microcontroller system is not required. The Opal RT has more than enough firepower for what we need to estimate this coefficient. Moving on to the objectives page here, Kelby's going to take over.
Okay, so here are the objectives / requirements / specifications of the project. Our overall objective is to develop an energy storage-based system to estimate this inertia constant. We have two requirements. We have integrate the hardware components of this system and implement a software algorithm that will calculate this inertia constant. Back it up a little bit, we have specifications. So for this first part, we have to generate this active power signal to disrupt the system. And then we also have to receive these voltage and current measurements from the system with sensors. And the specifications for the second part, we have to read these currents or these measurements of voltage and current. We have to output this inertia constant via Opal RT, and it has to be within plus or minus 10%. In practice, we have this broken up into two different parts, but in practice, this is not how we will be doing this. It just the way with planning and stuff, it's easier to look at it that way. So for our project, we have a couple constraints here. We're limited to using the voltage sensors and current sensors provided by the sponsor and the Microgrid Lab. We have to use the Xantrex inverter or a power amplifier that's also provided by the sponsor. And then we're also constrained to using the Opal RT system and the Microgrid Lab to estimate our estimation algorithm.
All right, moving on to our solution. How are we going to actually implement this process? We've talked a little bit about it on each slide, but we're going to put it all together here. And I have some animations in this slide, so hopefully they work. First, we have the lithium ion phosphate battery and the inverter charger. These are going to work as a combination, and they will be communicating with the Opal RT via CAN bus. That's what we'll be using to send the excitation signal to perturb the system. The genset and base AC load are just there to simulate a small scale power system. In practice, it would obviously be a much larger power grid. And all those connect through the AC bus to the Opal RT. And those are connected up via voltage and current sensors. And those measurements will be going into the Opal, processed through the software algorithm, and we will determine our inertia coefficient in real time. So I kind of sum that up on a page here. Step one is to perturb the system using CAN communication between the Opal RT and the inverter battery combination. From this, we will be able to measure the voltage and current readings of the system, almost like an impulse response. When we send that disruption signal, we'll get a response voltage and current we can measure. And those values will be sent to the Opal RT for processing. We process it through our algorithm. And then we should be able to spit out the system inertia constant in real time. And that is a very, very broad overview of what we'll be doing.
So I'll be talking about the project documentation and the budget. So upon request from our sponsor at Sandia, they would like a research paper describing our findings and the validation of the system that we will be using. Hardware-wise, they would like to see a functioning prototype of the system or of our power system within the lab. They'd also like to see the simulation code from the Opal RT interface for the software. With the anticipated budget, we have $100. Most of the material is already in the labs, so we don't anticipate using much of the budget at all, but we'll see what happens as we continue through the semester. But next we'll be talking about the Gantt chart. So take it away, Alex.
All right, moving on to the Gantt chart and the milestones. Just gonna give a brief look at our track here. We finished our rough draft and completed our charter, submitted October 9th, for the due date. And then in practice, this hardware and software will be developed in tandem, but for the purposes of keeping us organized, we will be using a due date on the initial hardware integration side of November 22nd, so right before Thanksgiving break. Hope to be done. Being able to send an excitation signal to the inverter and communicate through that CAN bus. And then pushing forward, the software algorithm implementation is going to be probably the most challenging aspect. We're doing research on that now, and there will be more to be done. So we're looking at that around mid-March, and then there'll be the final testing and all that stuff. And then the final deadline will be April 19th, as there is no real timetable for next semester yet, but for a general idea to keep us online, that's what we will be doing, be planning for anyway. So with that, that concludes our presentation. Thank you for listening. We're now going to open it up for some questions, so go ahead.